Okay, in my presentation today, I'm going to try and figure out how to advance the slides. I'm going to talk about how from all of these LSPIV free surface measurements that we can start to look at the turbulence velocity field to infer some important flow parameters. I'm going to talk about how we can, from the largest depth scale eddies that we see in these free surface turbulent velocity fields, we can infer the flow depth and the volumetric flow rate. I'm going to talk about how we can take advantage of the turbulence cascade to look at dissipation, and from that we can infer the bed shear stress. And when we start to combine this information, we can start to look at things like mean streamwise velocity vertical profile. So that's a quick overview of what I'm going to be talking about today. All of this work is captured in these 4 papers, which I'm going to upload the papers themselves into the chat at the conclusion of my presentation. Trying to advance the slide. Okay, so I want to start off by first talking about the physical basis for this work that I'm going to be presenting. If you look back into the open channel flow literature, you'll see like back in the day, they did a lot of experiments looking at deep open channel flow cases versus shallow open channel flow cases. And the way that they were able to designate between these two was by looking at the channel aspect ratio. And what they found for the shallow open channel flow cases that had an aspect ratio that was greater than 6, they found that there were in these shallow open channel flow cases, that there were large scale eddies that were present on the surface that were depth scale. And so they're impacting the entire water column. And they found that the geometry of these eddies basically scaled with the flow depth, as you can see in these 2 pictures here. And the way that they were able to tell that the geometry scaled with the flow depth is because they could see them on the surface. They impacted the surface, which you can see in this figure right here. So Todd Cowen, who was my PhD advisor when I was at Cornell, had the idea that perhaps we could leverage these large scale eddies to develop a remote method of predicting volumetric discharge and flow rate. Okay, and so that's where I came into the picture. For my PhD, I did a series of experiments in our wide open channel at Cornell University. This is a picture of the channel. It has glass walls. This is a schematic of the channel. I conducted 16 experiments in which I systematically varied the flow speed and the flow depth, giving me that all-important aspect ratio that classifies me in the narrow open channel flow regime. I added a rough gravel bed to half of the channel so that I could start to look at increased bed friction and how that impacts the flow. I conducted several cases for the rough gravel bed, and then I built this asymmetric compound channel just to give me some experience with variable bathymetry. We have in situ measurements provided by an ADV, and we also have ultrasonic transducers on the return pipe flow to provide an independent estimate for volumetric discharge. To characterize the free surface, we use an LSPIV technique. The technique that we use is very similar to what has been discussed in this workshop, so I'm not going to spend any time on this, but what I will say is for the experimental cases that I'm presenting today, for each case, I have over 4,000 image pairs, and that has implications for the field implementation of the methodologies that I'm going to be presenting today. So if we're trying to leverage these depth scale eddies to remotely determine flow rates and flow depth, the most logical way to quantify the size of these eddies is to look at something called the integral length scale. And this is the integral length scale. The integral length scale is the integral of the normalized autocorrelation coefficient, which is this fraction right here. Basically, this numerator is the covariance between the velocity fluctuations. And what you see around eddies is that the velocity fluctuations are correlated with each other. The covariance picks up on this physics. It tells me which spatial area. It tells me what the spatial area is of the velocity, that the velocity fluctuations are correlated. I normalize this, integrate. I have a robust method of estimating the size of the eddies that are on the free surface. When I did this in my open channel flow in my experiments, what I found was when I calculated the integral length scale as a function of when I calculated the integral length scale from my free surface turbulent velocity field measurements, I saw that there was a correlation with flow depth. This is the integral length scale. This is plotting across the normalized channel width. In pink are my 6 centimeter cases, blue is my 10 centimeter cases, red is my 15 centimeter flow depth, and my 20 centimeter flow cases are in green. You can see that the integral length scale is scaling with the flow depth. Similarly, for the asymmetric compound channel, over this variable bathymetry, you see that the integral length scale is responding to that change in bathymetry. When I take the mean of the integral length scale over the central core of the flow, neglecting what's happening near the corner walls, when I take the mean of the integral length scale and I plot that as a function of flow depth, I get a very strong relationship between the integral length scale and the flow depth. And what this means is, if I can calculate the integral length scale on the surface, I can relate this to the flow depth in my calculation of the volumetric discharge. And in this manner, I'm able to remotely predict volumetric discharge. I have my predictions on this axis. You have the in situ independent estimate of volumetric flow data. And you can see that I get really good agreement between the two. And so that was the contribution from the first paper. In the second paper, we started looking at turbulent spectra calculated from the turbulent velocity fields on the free surface. And what turbulence theory tells us is that there's an energy transfer region from the large scale eddies to the small scale eddies. And in that region, in this -5/3 region, the turbulent spectra that we can calculate dissipation from the spectra in that region. And so I have here, this is my turbulence dissipation. The smooth line is my turbulent spectra calculated from the free surface. And this kind of squiggly line here is my turbulence spectra calculated from the ADV. This is for one particular case, and you can see that I get really good agreement here between the two, as you would expect. And I've got this -5/3 region here. So I can calculate dissipation in this turbulent transfer region. And when I calculate the dissipation, again, I'm getting really good agreement between the LSPIV and from the ADV cases, as you would expect, given this behavior in the spectra. So what does dissipation have to do with bed shear stress? Well, I looked back into Nezu's 1977 dissertation, and he provided this universal relationship for how the dissipation varies throughout the water column. This is his expression right here, and you can see that I've plotted my data against this relationship, and my data bear out that this relationship is universal. Now, this does involve an empirical constant. Nezu fit his data to the empirical constant, and I did likewise. The fourth paper in the 4 papers that I'm going to be uploading today addresses how you can remotely predict what this empirical constant is, and it's related to how the turbulence intensity varies throughout the water column. So we've addressed that and making this a truly remote method. So if you look at this expression, Z on H is the normalized flow depth. That's my independent variable. I have a method for predicting this empirical constant. We know the flow depth. What I did was I took this relationship. This is the friction velocity. I took this relationship, I rearranged it to solve for the friction velocity, as you can see here, in this expression right here. And I plugged everything I know into this bracket. And in doing this, I now have a remote method of predicting the friction velocity. Here are my predictions on this axis right here. Here's my friction velocities estimated from the ADV profiles themselves. And you can see that I get really good agreement between these two. And so once you have the friction velocity, it's a fairly easy task to calculate the bed shear stress. And when I started looking at my estimations for the bed shear stress plotted, particularly for the rough bed cases, I see the types of trends that you would expect. There's enhanced bed shear stress over the rough bed case. So that's a contribution from the second paper. Lastly, I want to talk about this velocity index, this alpha coefficient that has come up a number of times in this workshop. So the volumetric discharge should ideally be calculated with this depth average velocity. However, most of us in this workshop have been calculating velocity at the surface and using this velocity index to relate the surface velocity to the depth average velocity. And if you look in the literature, this velocity index takes on a bunch of different values. And so I think most of you all would agree with me, if we had a remote method of predicting the mean streamwise velocity profile, if we could do that, we probably wouldn't even bother with this velocity index method. We would just calculate the mean streamwise velocity profile and just calculate the depth average velocity from that. So that's what I set out to do. And in looking at how we describe the mean streamwise velocity profile, there are two ways to do this. There's the velocity profile law and the log-wake law. And when I plot my data against all of these laws, my data support that both the velocity power law and the log-wake law are applicable for open channel flow. But in thinking about how to remotely predict these profiles, when I look at the log-wake law, there are really two unknowns here. There's two things that I don't know a priori. I don't know what this integration constant is, and I don't know what this wake strength parameter is. However, when I look at the velocity power law, there's a lot of things here that I know. This Umax is the surface velocity in open channel flow. And the Z on H is the normalized flow depth. That's the independent parameter. I mean, I know that. And U as a function of Z, that is what we are after. So if I can remotely predict M, this power law coefficient, then I have a way of describing the mean streamwise velocity profile throughout the water column. So that's what I set out to do. And I started digging through the boundary layer flow literature to kind of help me out with this problem. And as most of you know, open channel flow is just a turbulent boundary layer with a free surface. So we can leverage that rich history of research in attacking some of our problems. So I took my free surface friction velocity values and I recasted it into the skin friction coefficient, which is something that's heavily used in the boundary layer flow literature. And the skin friction coefficient is basically, it's a normalized bed shear stress. And so I took my friction velocity values, I put them into a skin friction coefficient. I started digging through the literature and I found that the skin friction coefficient is related to the shape factor. The shape factor, if you recall from your freshman year or whatever, I guess junior year fluid dynamics or undergraduate fluid dynamics class, the shape factor is the displacement thickness divided by the momentum thickness. It's this ratio right here. Basically, it's describing what this profile looks like. It's describing the dynamics of this profile. So this simple relationship, you can see from this boundary layer literature, it holds in the boundary layer literature. And when I plotted my open channel flow literature, the data hold, and the data demonstrate that this relationship holds. So this G is I don't have enough data at this point in time to say whether or not G is an empirical constant or if all of our data, if all of the open channel flow data are going to, like what that value of G is going to be. But so that's something that I'm pursuing moving forward. So having this shape factor there's a lot of information here. And what I found was that, in digging through the literature, the shape factor was related to this power law coefficient. And again, my data bear out this relationship. So I now have a remote method of predicting the power law coefficient. And so if I can predict the power law coefficient, I can predict the mean streamwise velocity profiles. Here are my results for the predicted mean streamwise velocity profile plotted against my in situ measured with the ADV. And here again, you can see that I get really good agreement between the two. What's really cool about this method is that probably most of us are using the index velocity at one particular location across the channel. But now I have a method of plotting how the index velocity changes across the channel. And in doing so, I'm able to improve my volumetric discharge calculation using all of this information as opposed to one data point. With that, I will conclude. I'm not sure how I'm doing on time, but I'm happy to entertain any questions if you have any.
You're doing very well, Erica. Okay, so who has some questions for Erica?
I do have some questions if I can.
Yeah, go for it, Julie.
Erica, fantastic presentation, very nice,
Thanks.
thank you. I was just wondering, so When an eddy approaches the free surface, there's a blocking layer basically where velocity is redistributed and the scales as well are modified from vertical to horizontal. So did you try and see how that those scales were changing throughout the water column? And did you see, because I would expect a strong effect of fluid number, to some extent also of surface tension?
Yes, so that's an excellent question. That's something that I didn't have time to get into our fourth paper, but in looking, when you look at the turbulence intensity value, if I understand what you're saying, that when you approach the free surface, you have your streamwise velocity, the vertical velocity fluctuations trying to get through the free surface are redistributed into surface parallel velocity fluctuations. So the turbulence intensity that you measure on the surface is not the same. There's a sort of a modulation that happens at the free surface that predicts, it's not the same as what you see in the water column. And so the fourth paper discusses this. And what we were able to do is we looked at the divergence. Actually, I have a quick slide, a backup slide. We were able to look at the surface redistribution related to the divergence that we see on the surface in order to predict how the velocity fluctuations are affected by the free surface. So that's covered in the fourth paper. Here's just a brief schematic of how we were able to predict that change in the turbulence intensities at the free surface. So that's something we think about, we've thought about. There's a paper on it, and I will upload that in the chat when I'm done with this presentation.
Thanks, thank you.
Perfect. Any further questions for Erica?
Yeah, Alex. Erica, very nice presentation, and yeah,
Thanks.
I think that it's a great objective to be able to measure all these parameters from the free surface. But if I understood correctly, and maybe I didn't, a major hypothesis is that the vertical velocity distribution follow a log law. And in a lot of situations in the field, the vertical distribution is not log because to wind effect, for example, or for some meandering effects. Mm-hmm. And so how do you think we can go also through those particular situations with when the profile is not log?
That's a really interesting question. Certainly with the USGS, they try and pick out sites that are perfect. In essence, in sites that you don't have meandering, you don't have some of these features. I'm not really sure at this point in time how I would handle that. Is something that I would have to think about. Is definitely the focus of my ongoing research efforts. But hopefully you agree with me that this is a great first start. I mean, I do think it works very well in the lab. There's a lot of work still to be done in terms of applying this to the field, because the field is much more complicated than what's happening in the laboratory. So I would like to see it done. I don't, at this point in time, I don't really have, especially like for deep open channel, like some rivers are a little bit deeper than the aspect ratios that I have. Specifically Blair's example, her aspect ratio is probably a little bit bigger than mine. How do some of these techniques work? That's an outstanding research question.
And do you have any plan about applying this method on the field? I remember the paper with Martin Dittert on trying to apply the method on some field measurement, but do you have new project about some application on the field?
Absolutely. I just got funded to do some of this work in the field, and I've done some preliminary research in the field. I think getting turbulence right in the field is an outstanding, it's difficult to do. And so that's the order one. It's the first thing that we need to tackle, is making sure that we've got turbulent velocity measurements. We've got them correct in the field. It's very difficult. Some of the infrared techniques that Todd presented is a pretty good way to do that. And also waves can kind of impact the turbulence measurements. So I feel like that's the first thing that needs to happen. But it's going to take a couple of years. Give me like 5 years, and then we'll have this conversation again.
Thanks.
Sure.
Can I sort of add to, I think Alex kind of asked the question I wanted to ask, which is about the field. But I'm wondering, like, we have so many ADCP data sets now, that could they not be used to help inform this? And you know, my thinking was if we could collect ADCP data sets and then find a way of sort of characterizing the surface turbulence and just collecting lots of this and giving it to you.
Yeah.
But how
That
could
would
we
be very
characterize the
helpful.
surface? Could we shoot videos? Could we do time series of stationary ADCP profiling? What, you know, what would be a useful set of data?
I mean, more data would be useful. I mean, certainly, I mean, I don't see us getting around, like, we're going to need ADCP data. We're going to need all types of, you know, surface. I need as much data as I can get for as many different conditions as you know, as we can think of.
But how do we characterize the surface turbulence in a way that's useful to you, I guess, especially as non-experts in the field? So like, is a short video useful, or is leaving the ADCP stationary and profiling for 5 minutes so it's picking up the sort of turbulence that it can detect, understanding beam spreading and all the other issues that are there?
So the type of data that's useful for me is, I mean, in situ measurements for as long as possible, and also, you know, surface measurements for as long as possible. I presented what I talked about very early at the talk, that all of the results that I presented today, there are 4,000 image pairs. That's a lot of data. And that's, you know, that's in order to get the turbulence right, you need a lot of data to clearly resolve the mean and then to clearly resolve the turbulent velocity. So as much data as, you know, my computer can hold is what I would like. And in situ
Todd's kind of suggesting my questions a bit null anyway, because ADCPs aren't well suited. But I mean, I guess you can pull out individual beam velocities from the ADCPs and so on. But yeah, I think it was more about training that understanding of the velocity profile, because that's the thing with, at the end of the day, as a hydrologist, I'm not really interested in turbulence. I'm just interested in how it can be used to give me the velocity profile, which is something I'm very interested in that. So if by finding a way to give you something you can use, even as a very broad brush and rough indicative sort of indication of the surface turbulence, and we've got that velocity profile, I suppose is what I was thinking. You know, you can start to link the two and see in the field, like Alex said, where things are complex, you know, how robust it is.